Since December 2021, the James Webb Space Telescope has unlocked various secrets of our universe, from providing newer images of galaxies taken by the Hubble Space Telescope to enlightening experts on supernova remnants and peering into the early universe. The spacecraft has already discovered so much. And in the latest observation, the powerful Webb telescope has just captured a new deep field view of the universe, which is a look into some of the farthest reaches of space. In Webb's image, the hundreds of objects you can see are galaxies among the black ether of the cosmos, each teeming with stars and planets. Many are spirals, like our Milky Way galaxy. The deepest ones appear red, as the expanding universe has stretched their light into longer wavelengths of red light. But that's not all. This view, which looks back at galaxies billions of years ago, because it takes that long for such old light to reach us, reveals several ancient galaxies and the black holes at their centers merging just a couple 100 million years after the Big Bang created our universe. Join us as we dig deep into new Webb telescope photo that truly boggles your mind. At the start of everything, the cosmos grew at a truly terrifying rate, expanding exponentially. Space begat space begat space. Reality was stripped of all form by space's expansion, becoming a tenuous, near-featureless void. If you could have sat on an atom, though there were no atoms, not yet, and gazed out at the rapidly expanding universe, you would have seen nothing, only a freezing, suffocating darkness. The remorseless stretching of space would have carried all other objects far out of sight, faster than the speed of light, beyond an unreachable horizon. Paradoxically, as space expanded, the world visible to any would-be observer shrank to a tiny, inescapable nutshell, binding every speck within its own isolated sphere of nothingness, separated from all other such specks by an ever-growing void. This age of extreme expansion has been given a rather mundane name: inflation. How long inflation went on, we do not know. It could have been a mere instant or an eternity. In all probability, we will never know. Nor are we likely to discover what, if anything, came before it took hold of the cosmos. Any traces of earlier epochs have been erased by the growth of space. But we do know that at some point inflation ended, and as it ended, the universe roared into being. As the force that drove inflation dwindled, its power birthed innumerable particles, filling the gasping void with a searing subatomic fire, the primordial plasma from which all objects in the cosmos would later form. From darkness, light. Within a trillionth of a second, the forces of nature came into existence, and with them the first and greatest blaze of light in cosmic history. Though inflation had ended, space was still expanding, albeit at a less ferocious rate. As the cosmos continued to grow, the primordial fire began to cool. Elementary particles, the building blocks of everything yet to come, fused to form the hearts of the first atoms. Over the next few minutes, the nuclei of the first chemical elements were forged: hydrogen, helium, and lithium. For around 380,000 years, the infant universe was filled with an incandescent fire, cooling slowly as space continued to swell. Then, at a critical moment, the temperature dropped low enough to allow electrons to wrap themselves tightly around wandering atomic nuclei, forming the first whole atoms. At this moment, the primordial flame went out, and darkness fell throughout the cosmos. A long, dark age began. For hundreds of millions of years, the universe was filled by a warm hydrogen fog. But in the darkness, the first seeds of structure were gathering. Slowly at first, then faster and faster, hydrogen and helium were drawn under gravity into ever thicker clouds. As these clouds grew dense, they also grew hot. At last, somewhere in the unsearchable reaches of space, the pressure at the center of one cloud became so intense that it ignited a nuclear fire, the spark of the first star. Light flooded back into the universe, and the Dark Age ended with a cosmic dawn. Soon, the universe was filled with stars, bright points of light in the slowly expanding dark. Gathered in the first galaxies, they forged chemical elements never seen before. Carbon, oxygen, nitrogen, iron, and many more were scattered through space as these first stars died in blazing supernovas. From their glowing embers, new generations of stars were born, and yet more elements were forged. A continuous cycle of birth, death, and rebirth. Around 9 billion years after the cosmic dawn, in an outer spiral arm of one of the hundreds of billions of galaxies now spread through space, a new star flickered into light. About it circled a fleet of worlds, and on one rocky sphere, inert matter somehow came to life. Under the guidance of dumb physical forces, atoms arranged themselves into ever more complex organisms that grew, multiplied, and evolved. For billions of years, the pale blue orb teemed with living things, species emerged and perished, and the dance of evolution went on. Until, at last, humankind stood on the surface of the earth, gazed up at the stars, and wondered. This story of the cosmos, its origins and its history, has been gradually pieced together over centuries by the collective effort of thousands of people. The fact that modern science allows us to speak with such confidence about events so remote in time and space that they defy imagination is surely one of the greatest achievements of our species. Particularly when you consider that this story was assembled by peering and prodding at the universe from a rather restricted vantage point on the surface of an insignificant little rock hurtling through space. But while we know how the universe began, the data we have amassed in both particle physics and astronomy tells us that we still only know about a tiny fraction of the universe. Looking at the sky, we observe that on the largest scales, matter is organized into galaxies and clusters of galaxies. Galaxies contain stars, planets, and gases. All the visible universe, the Earth, Sun, stars, and galaxies, everything that makes us, is made of protons, neutrons, and electrons bundled together into atoms. Physicists have developed an impressive body of knowledge about the fundamental particles and forces that characterize the ordinary matter around us. Centuries of discovery have shown that apples fall from trees for the same reason that the Earth orbits the Sun, and that the Earth is not at the center of the universe. It is a simple and elegant picture. The quest to answer the most basic questions about the universe has reached a singular moment. Astrophysical and cosmological observations have revealed that our picture of the universe is incomplete. Perhaps one of the most surprising discoveries of the 20th century was that ordinary matter makes up less than 5% of the mass of the universe. The rest of the universe appears to be made of a mysterious, invisible substance named dark matter, and a force that repels gravity known as dark energy. The exotic unknown substance named dark matter doesn't appear to absorb, reflect, or emit light, rendering it invisible. Since dark matter interacts very weakly with normal matter, its existence is inferred due to its gravitational effects on galaxies. Its fingerprints appear only when we look to the sky at the galactic and supergalactic scales, at about 10 million times the distance between the Earth and the Sun. According to physics, stars at the edges of a spinning, spiral galaxy should travel much more slowly than those near the galactic center, where a galaxy's visible matter is concentrated. But our observations show that stars orbit at almost the same speed, regardless of their distance from the center of the galaxy. This puzzling result only makes sense if we assume that the boundary stars are feeling the gravitational effects of an unseen mass, a halo of dark matter enveloping the galaxy. The existence of dark matter could also explain some optical illusions that astronomers see in the deep universe. For example, there are pictures displaying strange rings and arcs of light. These can be explained if the light from distant galaxies is distorted and magnified by massive, invisible clouds of dark matter, in a phenomenon known as gravitational lensing. The radical conclusion that the universe is filled with invisible and nearly undetectable matter can be compared to Copernicus's identification that the Earth is not the center of the solar system. We have established that we don't know what most of the universe is made of. Just like ordinary matter, dark matter also originated from the Big Bang. The amount of dark matter produced in the Big Bang has influenced the evolution of our universe. Similar to ordinary matter, dark matter isn't distributed across the universe evenly. Areas of the universe that had slightly more dark matter, and so more gravitational pull, attracted more matter, leading to the creation of the first stars and galaxies. The cosmic web we observe today is a snapshot of the dark matter distribution in the early universe. This mysterious dark matter acted as a hidden hand, guiding the growth of galaxies. Exploration of this unknown new universe necessitates the discovery of the laws of physics underpinning the fundamental particle nature of dark matter. The James Webb Space Telescope may have shed new light into dark universe. Some of the telescope's recent pictures have turned up 3 potential dark stars, ones powered by dark matter. That's the invisible stuff that makes up most matter in the universe. Scientists first proposed the existence of dark stars in 2007. The idea came from a team led by Catherine Fries, a cosmologist. She studies the universe at the University of Texas at Austin. According to Fries, if dark stars exist, they would be very weird-looking. The sun and other normal stars make light and heat by smashing hydrogen atoms together under immense pressure. When these hydrogen atoms fuse together, forming helium, they give off lots of energy. This process, called fusion, powers all the stars we see today. In contrast, dark matter would power dark stars. Scientists aren't sure precisely what dark matter is or how it works. We know only that it exists, because dark matter's gravity tugs on stuff we can see, such as galaxies. But it's possible that dark matter also can interact with itself. When 2 dark matter particles collide, they could destroy each other. Like fusion, that annihilation could produce enough light and heat to power a star. Dark stars can't form today. There's just not enough dark matter around. But these celestial bodies might have formed in the infant universe. That might be a few 100 million years or so after the Big Bang. Dark stars would have formed from clouds of hydrogen and helium. Gravity would have drawn these 2 elements together, along with any dark matter nearby. As the dark matter particles got closer, they would start annihilating each other, producing heat. That heat would keep the cloud of hydrogen and helium from collapsing completely to form a normal star. This would work similarly to the way heating the air inside a hot air balloon keeps the balloon inflated. Since dark stars wouldn't compress into tight balls of gas as normal stars do, they could grow to huge sizes. They might be up to 10 times as wide as the Earth's orbit around the Sun. That's over 2,000 times the width of the Sun itself. The biggest dark stars could be millions of times as massive as the Sun. They also could be billions of times as bright as an entire galaxy. That might even be bright enough to be spotted by James Webb. This giant telescope orbiting Earth looks for very ancient, distant objects. To look for dark stars, Fries and her colleagues searched the catalog of objects that James Webb has identified as being from the early universe, or from nearly 14 billion years ago. They found adequate data about electromagnetic emissions for only 9 of those objects. Of those 9 deemed useful for study, 3 were a good match to what a dark star would look like. They known as Jades, GS, Z13, 0, Jades, GS, Z12, 0, and Jades, GS, Z11, 0. These objects had high redshifts, meaning they emitted light skewed toward the red side of the electromagnetic spectrum, which is a sign of old and distant objects. That light was also possibly from a single point source, such as a star, rather than a fuzzy galaxy. That means those three real-world objects look how scientists would expect dark stars to look. And that's freaking cool. Detecting these dark stars would provide a new type of evidence that dark matter exists. It could also hint at how this mysterious substance works. Knowing that dark matter could annihilate itself would be really, really powerful, says Tracy Sladier. Not only that, dark stars also might help explain the origins of supermassive black holes. These cosmic monsters, with millions or billions of times the mass of our sun, sit at the center of many galaxies. Smaller black holes can form when giant stars die and collapse. Scientists aren't sure how supermassive ones form, much less get so big. Dark stars could provide one answer. Once all the dark matter inside a dark star has annihilated itself, the remaining cloud of hydrogen and helium would collapse. That cloud would still be millions of times as massive as the sun, so its collapse would create a huge black hole. Those giants might later merge over time into supermassive black holes. In short, our journey into the cosmic dawn continues, with the James Webb Space Telescope as our guide. With each discovery, we move closer to unveiling the secrets of the early universe and gaining a deeper understanding of the forces that shaped the cosmos. The high redshift galaxies observed by the James Webb serve as time machines, allowing us to peer into the past and draw nearer to the enigmatic origins of our universe. The cosmos unfolds its mysteries, and we, as explorers of the unknown, stand at the precipice of discovery. A piece of good news: scientists using a NASA space telescope have discovered a tantalizing world. It's about the size of Earth, sits remarkably close to our solar system, and could be comfortable for life as we know it. The extrasolar planet, or exoplanet, named Gliese 12b, orbits a small and cool red dwarf star located just around 40 light-years from Earth in the constellation Pisces. The exoplanet, which the team found with NASA's Transiting Exoplanet Survey Satellite, or TESS, is estimated to have a width around 1.1 times that of Earth, making it similar to our planet as well as Venus, which is often called our world's solar system twin. Gliese 12b orbits its star, Gliese 12, so closely that its year lasts just 12.8 Earth days. However, because the red dwarf Gliese 12 is just around a quarter of the size of the Sun, it is also much cooler than our star. This means that, even though Gliese 12b is at a distance from its red dwarf parent equivalent to just 7% of the distance between the Sun and Earth, it still is in its planetary system's habitable zone. Also known as the Goldilocks zone, the habitable zone is the region around a star that is neither too hot nor too cold for planets to host liquid water, a vital ingredient for life as we know it. Though, importantly, the two teams behind the discovery of Gliese 12b can't yet say for sure if it has an atmosphere. It therefore remains unclear if the world could be habitable, but the researchers have some cautious optimism. As University College of London scientist Larissa Palathorpe, who co-led the research with University of Southern Queensland astrophysicist Shishir Dholakia, said, "The majorly interesting thing is that this is a planet that's really nearby. In fact, it's one of the closest transiting planets to Earth. It's either in the habitable zone of its star or it is right on the edge of it, so it could be habitable." Scientists spotted Gliese 12b as it crossed, or transited, the face of its parent red dwarf star. These transits cause tiny dips in light that TESS is adept at spotting. Palathorpe added that, when the team went into this project, they didn't know what the orbital period or the size of the planet would be for sure. To find it to be such a similar size to Earth was kind of a lovely surprise, she continued. So that was a really nice thing to be able to nail down, but I think especially knowing that, in terms of habitability, it could lie between Earth and Venus is really exciting. Gliese 12b receives around 85% of the radiation that Venus gets from the Sun, but is thought to have a much cooler surface temperature of 107 degrees Fahrenheit, 42 degrees Celsius, compared to Venus's surface temperature of 867 degrees Fahrenheit, 464 degrees Celsius. Though Earth and Venus are both in the Sun's habitable zone, one can support life and has a favorable atmosphere, while the other is an inhospitable hellscape with temperatures hot enough to melt lead. Studying Gliese 12b could help us understand why this is the case. In the words of Palethorpe, Gliese 12b could teach us a lot about how our own solar system has developed as well. The team will now investigate whether Gliese has an atmosphere, but early indications are that if it does, that atmosphere would be relatively thin. Perhaps surprisingly, however, the lack of a thick atmosphere is good news for the planet's habitability prospects. As Palethorpe's fellow UCL researcher, Vincent Van Eilen, said, "We know some planets have very thick atmospheres of hydrogen that cover the entire planet. This very thick gas layer is actually bad news for habitability. Usually, these planets are 2 or 3 times the size of Earth. Gliese 12b is the actual size of Earth, so it probably doesn't have this very thick atmosphere. However, even if Gliese 12b does not have an atmosphere, it could still be an important test subject for advancing our search for life elsewhere in the Milky Way. That's because, as a red dwarf, the star it orbits happens to be the most common form of star in our galaxy, yet one we know relatively little about when it comes to red dwarf planetary systems. In the Milky Way, red dwarfs comprise the largest family of stars that are still fusing hydrogen to helium in their cores, a process that defines the so-called main sequence lifetime of a star. It is estimated that 60% to 70% of the stars in our galaxy are red dwarfs, like Gliese 12, and of the 30 stars closest to Earth, at least 20 are red dwarfs. It's interesting to know about planets around the small stars, what they might be like, and whether such planets could have life, Van Eilen added. Officially known as K-type or M-type stars, red dwarfs have between 7.5% and 50% of the mass of the Sun. This low mass relative to the Sun means such stars burn at a lower temperature, reaching only 3,500 degrees Celsius compared to the 5,500 degrees Celsius temperature of our star. For instance, Gliese 12 has a surface temperature around 60% that of the Sun. This lower temperature means that dimly shining red dwarfs can exist as main sequence stars for much longer than moderately massive stars, like the Sun can. And although the Sun is expected to live for around 10 billion years, red dwarfs are predicted to have lifetimes tens, or even hundreds, of times this period. Sometimes, that figure can extend to trillions of years. What this means is life would have more time to develop on planets orbiting red dwarfs than it would on planets around larger main sequence stars. But it isn't all good news for the prospects of life on red dwarf orbiting exoplanets. Though they are cooler than the Sun in their stellar adulthood, red dwarfs are believed to be much wilder than our star. This class of star is believed to be highly magnetically active, blasting out frequent and powerful flares of high-energy light in the form of X-rays. These X-rays can violently strip the atmosphere of a planet close to a red dwarf. Additionally, recent research has suggested that even red dwarfs that remain placid for many years can suddenly erupt with superflares 100 to 1,000 times more powerful than the Sun's solar flares. These eruptions are more common in the youth of this stellar class, and are also capable of stripping atmospheres and boiling away liquid water, even in habitable zones. At the moment, though, both teams involved in the discovery of Gliese 12b think the red dwarf in orbit is relatively calm, which could be good news for the exoplanet's chance of possessing an atmosphere. The fact that red dwarfs are cooler than stars like the Sun, and thus their habitable zones are closer to the stars, actually makes detecting exoplanets around them a little easier for TESS and its transit method of planet hunting. As Palethorpe said, we have biases towards detecting planets that are close to their host stars, essentially, just because they transit more often. When we find planets orbiting red dwarfs because they're smaller stars, the dimming of the transit is bigger. Because red dwarfs are slightly cooler, the habitable zone lies closer to the star than it would for our kind of sun, which means we're more likely to detect planets in the habitable zone with TESS. The team will have to turn to other instruments than TESS to investigate this planet further. They will also switch to a different method of exoplanet detection to better define the characteristics of Gliese 12b. One is called the radial velocity method, which utilizes the tiny wobbles planets cause in the motion of their stars as they gravitationally tug on those stars. Scientists are already actively doing that as part of the high-accuracy radial velocity planet searcher for the Northern Hemisphere team, which is a radial velocity telescope. Then they've also got another proposal accepted with the European Organization for Astronomical Research in the Southern Hemisphere, which is another radial velocity telescope. And so, hopefully, from kind of the radial velocity observations, scientists will do this. In addition, Palithorpe and Van Allen also hope to be granted time with the James Webb Space Telescope to further investigate the planet's atmosphere. This is possible because as Gliese 12b transits the face of its star, light passing through its atmosphere will carry the characteristic fingerprints of elements in the atmosphere. This process is called transmission spectroscopy, and Gliese 12b is only one of a handful of temperate Earth-like worlds that are close enough to be examined in this way. The Webb telescope is currently conducting a similar investigation for the 7 Earth-like planets of the TRAPPIST-1 system, located around 40 light-years away. These planets resemble Gliese 12b, in that not only are many of them in the habitable zone of their star, but that star is also a small and cool red dwarf. When it comes to the possibility of Gliese 12b hosting life, the two scientists are extremely cautious. After all, it is early days for both our understanding of this world and methods that would be capable of detecting signs of life in an exoplanet atmosphere, even one so relatively close as Gliese 12b. As Palithorpe concluded, I think Gliese 12b will teach us a lot about life, but we can't say anything for certain. I think it's very exciting, and we should definitely look forward to more research coming out about Gliese 12b. It's not a bad place to start on a hunt for life. That's all the information that we have for you today. And don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.